let's start with the outstanding tough bit to get it over and done with. And that we looked a little bit on how particles interact with each other. We went as far by saying that AFM, for example, you could measure force interaction. You could measure force between an approaching tip or something on a tip and a substrate. And so I want to go a little bit further into that. So just to recap, so this is kind of a thing what we would like to see. We want to think about two molecules interacting with each other. And if two molecules would interact with each other, we can describe that with a pair potential, as in how two bodies would, interact on each other as function of the distance. And the main question is then, is there a common ground between intermolecular forces that hopefully you all know because you've studied already about 2.5 years of chemistry, so hopefully these things sound familiar. But how do I translate intermolecular forces to interparticle forces and intersurface if you have two large surfaces forces? So is there similarities, and what do I have to be careful with? And so how can we basically solve this or try to solve this? So the main thing is let's first make this time warp back. And we talked about it a little bit already. So we've seen this slide before, and we kind of realized that van der Waals was quite a clever guy, because in his PhD thesis, he realized that for gases, you had to take into account that molecules had their own volume. So he added a correction term for that, so which was B in this particular case. And he also noticed that molecules underwent an interaction with each other, and that interaction term he referred to as A. And on the basis of this, on the van der Waals equation, if you would look to standard thermodynamics, with that equation you can explain that a gas would condense into a liquid and even potentially could go to a solid state. And you could get the PVT diagram, as in the phase diagram, for gases and liquids. You could get a really good approximation for this using that, not too difficult expression. As a result of that, he got a Nobel Prize for this, which is quite nice. So, slightly different approach, extending on this interaction bit, was a person which is called Me. And he came up with a generic potential to describe interaction between molecules in this case. So the pair potential in this case had an attractive term, and attraction is defined as negative. Yeah? Repulsion is defined as positive. So it says minus, and it's a power law expression. Yeah? So it's A divided by the distance between these objects to the power n. As an attractive term, and then the B is a repulsive term, so it's plus B, and then it's divided by R to the power m. Now, a special case of this Me potential is the rather well-known Lennard-Jones potential, which is a 612 potential, which means that the attractive term scales with 1 over radius to the power 6, and the repulsive term scales with 1 over the radius to the power 12. So the repulsive term is like really steep. And you can imagine if you have two objects and you bring them really close, that you kind of have to push them into each other. And as a result of that, they repel each other. And R to the power 12 scales on the short range really steep. So it's a good idea to use something like that. Now the R to the power 6 term is often referred to as the van der Waals interaction. So why is R to the power 6 equivalent to van der Waals interaction? Now, if you take the van der Waals expression and you calculate some forces on that, this something to the power 6 is an important thing. So all I want to do is try to show you some molecular interactions that contribute to the van der Waals interaction. So the key message is they have to scale with 1 over the radius to the power 6, and they obviously then, in this particular case, they should be valid in the liquid or in the gas phase where things can move around freely. So this picture is taken from Jacob Israelachvili's book. This one is from the 2nd edition. There's a slightly graphically more enhanced picture in the 3rd edition. And hopefully you have seen this before, or at least you've seen the words before. You might not have seen the equations before, but have a look at this to the power 6 thing. So covalent interactions, so the actual chemical bond formation, yeah, so H2 or H2O, which is very complicated to describe. So you can calculate, you know, the specific bond strength, but in order to do this, it's not easy because you need to know a lot about the energy levels, and you know, electrons will get shared between oxygen and hydrogen in case of H2O. And in order to get a good idea of that, you basically need to be able to map this molecule pretty well. So there's no easy expression for this. So let's move one further down. Charge-charge interaction. So just think about a point charge, about, for example, a positive charge and a negative charge. They will attract each other. Yeah? So, and as a result of that, you can get a Coulombic energy related to that. And that is defined as the charge 1 times charge 2 times, well, this is in vacuum in this case, divided by 4 pi times r, which is like effectively if you go on a spherical type of interaction. And then you have the dielectric permeativity in vacuum, which is epsilon 0 in this case. If you do it in a real liquid, you got to multiply it with the relative value, so you get epsilon 0 times epsilon r, or the product of those two could just be epsilon. So you see that a Coulombic interaction scales with 1 over r, which means it's pretty long range, right? So from a relatively long distance, these two objects will feel each other. So if you were like a sodium chloride ion, for example, they will feel each other from, those two atoms will feel each other and attract each other from a relatively long range. And in order to calculate this, you use that particular expression. Now then you have a bunch of other expressions there, and you must have heard, hopefully, of a dipole, and maybe you've heard about an induced dipole. But let's just first have a look at what this means with respect to the dependence on the radius between these two objects. So, and we'll define what a dipole is a little bit later in case you have forgotten what that was. So, if I have a fixed dipole, which means a dipole that cannot rotate, and a charge, you see that it scales with 1 over r to the power 2. So that's not a van der Waals type of interaction. If you have a freely rotating dipole and a fixed charge, you see it scales with r to the power 4. So that one doesn't class either as a van der Waals contribution. A fixed dipole and a fixed dipole, as in those two things cannot rotate, so your molecules can't rotate, r to the power 3. And then you see a freely rotating dipole, so you have two polarized systems that can freely rotate, you see that scales with r to the power 6, 1 over r to the power 6. Well, that component is one of the three components that contributes towards the van der Waals interaction. And that component is called the Keesom energy. So the Keesom energy is dipole-dipole interaction, and it's one of the three that you need to, well, with one of the three components that describes the van der Waals interaction. So here's a few other ones. So you have a charged and a non-polar species, 1 over r to the power 4. Then you have a fixed dipole with a non-dipolar component, which scales with 1 over the power 6, but a fixed molecule means it can't rotate. So in liquids and in solids that vibrate things, that's not really realistic. So that one we forget about. Then we have a freely rotating dipole and a non-dipolar components. And then again, you see 1 over to the power r to the power 6. So that is the Debye energy. And is the second component that contributes to your van der Waals interaction. So you have an interaction between a dipolar, a polar molecule, and a nonpolar molecule, or a nonpolar atom in this case. So the last term is a term that is always present. And this might be the term that most people would identify as a van der Waals interaction term. And that's the so-called London dispersion, and the London dispersion energy, or more commonly now referred to as the dispersion forces and dispersion energy. And then you have two nonpolar components. So that is always there. Yeah? And that term also scales with 1 over r to the power 6. And then you have other interactions, so hydrogen bond interactions. Again, it's very complicated to describe, and generically scales with 1 over r to the power 2. So out of all of these interactions, there are 3 that we have to take into account if we look at van der Waals interactions. So if there are no charges, no fixed charges on your molecules or on your particles, those 3 components we have to have a closer look at. So we have the Keesom energy, the Debye energy, and the London dispersive forces. So this holds for anything. So 3 components. Okay. Now, what are these 3 things? So for this, we need to understand 2 concepts, which hopefully you've had before. So what is a dipole moment? Yeah. So imagine you have a molecule that can polarize itself. So for example, one side of the molecule is more electronegative than the other side. So basically, if you have a polar component, yeah, those molecules have got a fixed dipole moment. And the dipole moment effectively equals the charge separation, because one side would be more negative and the other side would be more positive. And effectively, the molecule is electroneutral, so that should spread out in this case. And then the distance between those points will define your dipole moment. And if you would go back to these expressions, that dipole moment is in there, right? So if I look here, for example, in my Debye energy, you have this minus u term in there, minus u to the power 2, which is, in that particular case, your dipole moment. Now, an induced dipole moment is effectively a molecule that is nonpolar, or it's the nonpolar component in a molecule. And the only reason why you would get an uneven charge distribution is because there's an externally applied electric field. So in that particular case, what you might have heard of is a molecule polarizable? Yes or no? So you impose an electric field, and as a result of that, you'll get a little bit of charge separation, delta minus, delta plus, and you get an induced dipole moment. So those 2 things are hopefully things you've heard of, but maybe not in a physical point of view. So what does this mean? So what about a dipole-dipole interaction? So imagine that one side is negative, the other side is positive. So say if the arrowhead is the positive bit and the other side, the arrow tail, is the negative bit. You can imagine that minus plus likes to align itself. Yeah? Because in the other case, you get minus plus plus minus, and the 2 pluses point at each other, and 2 pluses repel each other. So that's not an ideal scenario. So as a result of this, like the space average of this, because these things freely rotate, you get this expression. So you have the Keesom energy in this particular case, 1 over r to the power 6. And you basically, if you know the dipole moments of these molecules, you can fill in what this number is. So you can account for that. So the original papers, the original references are given below. So that's quite an interesting concept. So the same holds for a dipole-induced dipole interaction. We set an externally applied electric field. So the dipole is permanent, so you have minus and positive at the arrowhead, which basically means if you have a nonpolar molecule, it doesn't really like that plus charge there, so it basically effectively, temporarily, only because this other molecule with the permanent dipole is there, it will redistribute its charge. So you get a slightly negative charge closest to the arrowhead and a slightly positive charge on the other side. So now you have a dipole-induced dipole interaction, which is the Debye interaction. So in this particular case, the scenario on the left is the same as the scenario on the right. And again, this particular thing scales with 1 over radius to the power 6. And the absolute numbers come in if you know the polarizability of the molecule and if you know the dipole moment, which are things that are measurable. Yeah? So the difficult bit potentially is that, there might be a variety if you go to the dielectric constant in a medium. So this equation holds in vacuum, yeah, because you only have the epsilon 0 there. So, and again, below there, there's a little example of how large these forces are. So typically, we're talking of potentially on the order of kT. So then you have the induced dipole. So if you have two kind of nonpolar molecules next to each other, you can also imagine you get charge separation. Yeah? So in this particular case, you get delta minus delta plus is pretty a good arrangement for electron densities, for example. Anti-parallel is the same. So if they rotate, you also match plus minus and plus minus. So both of these things are quite interesting. So you can add them on top of each other, and then in this particular case, you also get the 1 over 6. So these are the dispersion forces that are always there. Yeah? And on top of that, you have potentially, if there's a polar molecule present, you'll have polar, nonpolar, and polar-polar interactions. So all these three together, whereas this one is by far the biggest, will form, well, in most cases, quite the most substantial one, will form the van der Waals interactions on the molecular scale. So that is the reason why people use a Lennard-Jones potential. The r to the power 6 was reflected in those three interactions. The key sum, the Debye, and the dispersion forces. That's where r to the power 6 comes from. And the absolute number, obviously, is A. And A you can measure with AFM. Now B, the r to the power 12 term, that's just a bit of a steep term. You could just say, okay, why is it not r to the power 13 or r to the power 14 or r to the power 24? And sometimes people do use that because effectively the minimum probably won't shift that much if you up the dose of that r to the power 12 term. So there are different potentials available. So people use 6, 12, or sometimes some screened ones. So it's not unique, but 6 is more justifiable than 12. So we've seen this plot before, right? So we've seen before that the interaction energy, which is V or sometimes W, the first derivative of that would be the force curve. And the force curve is something you can measure, for example, with AFM. So the Lennard-Jones potential, which is the one on the top left, is not always, sometimes you have other interactions there. You could have a permanent charge, and then on top of that you have Coulombic interactions. And sometimes there's other things happening, so you can get lots of different potential curves. So you can think of anything in these 6 scenarios, something that you could use in order to model. So for example, the steepest one you could be, okay, there's no attraction, there's no repulsion, or there's only steep repulsion, so you could just use a block function. Yeah, hard sphere is when they touch each other, is just infinitely up. That would be the simplest one. And in other cases, you can think of wiggly things like this. So the one, you know, on the bottom right, there is no attraction. That's when they come closer. There's just some repulsion term, and they can push a bit closer together. So maybe the surface has got some bound molecules or something that you really have to push hard before it goes up steep. And these particular things, so in picture D here, you could have a secondary minimum even, which means if there's a minimum there, that's a stable configuration where either particles or molecules can sit. So the Lennard-Jones potential for molecules is obviously only valid when you have those type of interactions. If you have Coulombic interactions on top, you have to take that into account. And the other thing is this A and this B term, you can potentially calculate with the equations I've shown you before, or you have to experimentally measure it. Now, let's just forget about, for a while, the repulsive bit. And let's just have a look at slightly larger distances. So r to the power 6 or less, 1 over r to the power 6 or less. So longer distances where this r to the power 12 term doesn't really matter. So we've hopefully, I've convinced you that for van der Waals interactions between atoms and molecules, the form would be some particular term, it's attraction, minus c, divided by r to the power 6. So, but now, what if I go to a particle? Because a particle is composed of more than one atom, and sometimes more than one molecule, or there's lots and lots of different atoms. So all these atoms in this particle will interact with all the atoms in another particle. So how do you solve that? And luckily, kind of people figured out that it's like an additive contribution. So if I would have one atom interacting with another atom, if this one atom suddenly becomes a sphere of 1,000,000 atoms, I have to match all the interactions of those 1,000,000 atoms with that one atom that's spaced apart. So you have to integrate these expressions for a particle-based system. So I just want to give you a feel of this. So I don't expect you to get all the details, but just the concept behind it, right? So here you have a macroscopic flat surface, which is this large chunk of gray thing on the left-hand side. And then you have one particular atom or molecule from a distance d from that particular surface. Now, in order to calculate the pair potential between these two objects, you have to calculate the interaction of that one single atom or molecule with the entire surface, all the atoms in the surface on the right. So in order to do this, you have to integrate over that entire body, which is displayed on the right. So if you would do that, effectively how they've done it here, because in one dimension you'll have a defined distance z, and the other thing they just use a cylindrical coordinate kind of xy block system, and they draw like a donut almost, right, which they loop round. And if you do that and you do the math of that, you'll end up with an expression that gives you the interaction as a function of the distance between the two objects. And what you'll see, it's slightly more complex than this n to the power 6. So you'll have n minus 2, n minus 3 times d times n minus 3 for n is larger than 3. And this n term for 6 would be then, if I would have a look at the van der Waals term, which means n is 6, then it becomes here, d is 3. So it scales with a certain term divided by d to the power 3, which is not the same as r to the power 6. So you see that the interaction between an atom and a flat surface becomes longer range. Yeah? So it takes a longer time. From a longer distance, the atom will see the surface. Now, obviously, you can do this for different geometries. So here you see the interaction between a macroscopic flat plate and a particle that's substantially large. And if you do the math then, which is not easy, you'll end up with this big chunky equation that's here marked as 10.4. And you see that this basically comes down to, well, it's an approximation actually in order to solve this. So only for distances where the distance between the particle and the flat surface is way smaller than the radius of the surface, you'll end up with that expression. So it's an approximation. So short distances, you'll end up, if you put the numbers in and you put the van der Waals term here in as n to the power n6, you'll end up with scales with 1 over d. Hey, this is interesting. So the interaction between a flat surface and a sphere scales with 1 over d. The interaction between an atom and a flat surface scales with 1 over d to the power 3. The interaction between two point charges or two atoms scales with, and r is the intermediate distance, which effectively is the same as d if you define it, scales with 1 over d to the power 6. So depending on the geometry, you get a different distance dependence. So, well, that's the other extreme case if the distance is really far. So if d is really, really large with respect to r, you get a different number. So it's even more difficult, right? So in this particular case, if you're really, really close between these two, it scales with 1 over d. But if you're really, really far away, it scales with 1 over d to the power 3. So that scaling factor is not even constant. Obviously, for two flat surfaces, you get another one, and then you end up with 1 over d to the power 2. So it looks like this is insanely tough. And luckily, two clever people figured out that there was a relatively easy scaling factor to interchange between all the different geometric setups. And that was Derjagan and Hamaker. Now, Hamaker was a really clever guy, and he figured out in 1937 how to solve this for two spheres. So two spherical particles interacting with each other. And he came up with this massive expression over there, which is an analytical solution to the problem given above. And effectively what it came down to was, it was like a preterm there for n is 6 in this case, and a very, very long, chunky term that basically said what the distance between the two particles were and the radii of the two spheres. And the little chunky bit in front is called the Hamaker constant. So if you have the charges in there, and if you have the London interaction energy in there, which in this case would be lambda, he called it lambda, then the van der Waals interaction, then that first bit was the Hamaker constant, and the geometric term is the stuff between brackets. So the question now was, is this geometric term, is that easy for different geometries? And then the only thing we have to solve is what is the Hamaker constant. So here you go. So this is a nice summary. So this summary is after all the maths, this is actually the thing that I want you to understand, which is that the interaction between atoms, two atoms, scales with 1 over r to the power 6, which is the van der Waals interaction for atoms. Now, if you make it macroscopic bodies, this inter-object distance, which is defined as d, the scaling law of that changes. So if you look at two spheres, for example, there, it scales with 1 over d. And then the term that's corrected there is r1 times r2 divided by r1 plus r2 is the radii of the two different spheres. So that doesn't look too chunky. It looks manageable. And basically, if you can't do an experiment with two spheres, so for example, if I would have a sphere on an AFM tip, and then I have a flat underlying surface, and I measure the force and I integrate that, I can come up with the W term. That would be minus a times the radius of the sphere divided by 6d. So if I know that one, I can calculate the two spheres one. So the only thing that I don't know is A. The rest is geometrically defined. If I have two cylinders that are parallel to each other, you get a different correction term. You have to know the length in this case of overlap. But again, it just comes down to a geometric term, a different scaling law for D, which is quite interesting, right? So the total energy depends on how you interact with these two things. So if my two cylinders are parallel to each other, you get d to the power 3 over 2. And if they're perpendicular to each other, I get 1 over 6 of 1 over d. So the scaling law changes in that particular case. So the nice thing now is, with different types of experiments, you can measure these particular pair potential interactions, either via force or via energy experiments. And the thing that is the most complex bit out of this is, what is A? And A is defined as the Hamaker constant. And the difficult bit is, what is the sign of A? Because we said in this particular case, if A is positive, all these terms would be negative, which basically means there's attraction. But what if A is negative? Then there is repulsion. So, and sometimes you can do some really bizarre experiments, and then you might get, you know, everybody thinks that van der Waals interaction is attractive, but that's not the case. It can also be repulsive. And the only thing that determines that is the sign of A, whether it's attractive or repulsive. So, there's this Russian Lifshitz theory, which is insanely complex, so complex that people didn't want to use it. It was developed in the 1960s, and basically what it was about was, like, for example, if we look at picture B, if I would have a charged object, then to a macroscopic surface, then you can create a ghost charge, an image charge of the opposite sign on the same distance on the other side of that boundary, so in the middle picture. So that sounds rather weird. And then depending on the dielectric constants of these media, you either get an attractive force, so it's like plus minus and they like each other, or it's the same and they repel each other. So that kind of baffled people quite a lot, because this was the missing link that sometimes people measured a Hamaker constant which was negative. So what do I want you to take away from negative or positive? Well, luckily the rules are not difficult. However, nailing the absolute value is difficult, so we stay away from that. But here are the rules, and they're not that difficult. So the van der Waals force between two identical bodies, as in two objects of the same chemical composition, in a medium, so either a liquid or a gas, is always attractive. So if I have a polystyrene particle and a polystyrene particle in water, that's attractive. However, if I have polystyrene and another particle of a different chemical composition, and therefore a different dielectric permittivity, it can be attractive or repulsive. So, and that's where you have to watch out. So now, when is it repulsive? Well, that's the next line. The Hamaker constant is negative, and therefore the interaction will be repulsive. So you have a repulsive van der Waals interaction when the dielectric properties of the medium between the two bodies are of the intermediate value between the dielectric constants of the two bodies. So you can look up what the dielectric constants are. If the liquid in which these two things are dispersed is in between the dielectric constants of body A and body B, the van der Waals interaction is repulsive. So for example, if I would have a particle dispersed in water and it approaches an air interface, then the dielectric permittivity of the particle generically is higher than that of water, could be higher than that of water, and then it would undergo a repulsive interaction at the air-water interface. So the last bit is that in vacuum or air, everything is always attractive. So there's no repulsion there. So these are, the thing to remember is that a van der Waals interaction is composed of three components. So the Keystone energy, the Debye energy, and the dispersion forces. The van der Waals interaction depends on the Hamaker constant. The Hamaker constant can either be positive, in which there's an attractive interaction, or negative, in which case there's a repulsive interaction, and it depends on the dielectric constants of the media, whether it's positive or negative. And then also that the force curves and the interaction curves depend on the geometry of the macroscopic objects. So two cylinders will interact differently with each other than two spheres. And you can correct for that in the Desjardins approximations that were shown in that table. So okay, so here are some, just some numbers. So people try to measure this. So the Hamaker constants, and this basically tells you something about the strength of the van der Waals interaction, right? So the higher that number, the stronger the van der Waals interaction. So, so you see here that, for example, in diamond, you have an extremely strong van der Waals interaction, whereas in other materials, it drops to way lower values. But what you also see is that people don't tend to disagree. So if you take the third do tend to disagree. So if you take the third entry here, it's quite a big difference, right? From 45 to 60.7. So, you know, you're 50% out. So it means that these things, you know, it's not always easy to measure this. So again, here you see a few more. So in vacuum and in water. So, and here the interest is a very interesting concept here. So here dispersed in water. So if it's a polystyrene particle, your Hamaker constant 1.3, yeah? Times 10 to the power minus 20 joules. If you make the same particle of the same size of gold, it's 30. So the van der Waals interaction between gold and gold in water is 30 times as strong as that of polystyrene in water, which means you have to have way more stability for these things not to bump into each other. So, and then you can see that silver is even worse, right? So to keep colloidally silver stable is way more difficult than to keep polystyrene colloidally stable. Not even to mention the other factors like density, right? Because obviously gold is very dense, 19.6, and if you blow that up large, then you have a density problem. So what effectively, if we just look at spheres, what it comes down to, and if all the spheres are the same size, the van der Waals interaction term reduces to the term on this equation here. So it's minus A, which is the Hamaker constant, which you can look up or measure, times the radius of the sphere divided by 12 times the distance, the surface distance between the two spheres. So that's the van der Waals term there. So this holds for distances that are smaller than the radius of the sphere, and otherwise it becomes a little bit more complex. So if the van der Waals interaction is attractive, we've seen before that in order for colloids not to bump into each other, we have to add a repulsive term. And this repulsive term, for example, could be charges. Yeah? So this now relatively simple end equation describes the attractive van der Waals term, which scales with 1 over the distance between the particles. So what about this repulsive term then, this Coulomb repulsion? Well, unfortunately, in high dielectric media like water, this is not easily solved. Because in water, you get counter ions and you get the buildup of a double layer, so you don't have effectively two charges. So you have to take that into account. So the electrostatic double layer, which hopefully you've heard of in electrochemistry a little bit in year 2, will tell you something like this. So you see the picture on the top left, and you see in this case I have a surface with a negative surface charge. So that's on the surface. And if I move away further from the surface, so my counter ions are my ions of opposite charge. So if I have a negative surface, my counter ions will be my cations. And you can plot what their concentration profile should be. So if I'm infinitely far away from my charged surface, obviously the amount of anions and cations is the same. Yeah? So that's why I end up with a flat line. And the flat line effectively is the concentration or the density, the charge density of those species. Now, if I come closer to this surface, you can see that an anion will be repelled from that surface, so you get depletion of that concentration, so it effectively drops to 0, whereas for the cations, obviously, you go up, because effectively, the entire thing should be charge neutral if I look from infinite distance to the surface. So you get two different profiles there. Now, the way how these profiles are built up is with two different things. So you need to know something about the electric potential. And the electric potential, you have a Laplace operator here, effectively can be calculated as a function of the dielectric permittivity and the charge density. So, which effectively for a spherical, well, for this particular type of system, is -4 times pi times the charge density over epsilon. Epsilon in this case could also be epsilon 0 times the relative permittivity. So for water, that would be 78 point something, if I remember correctly. Might be wrong there. So, so that, you need that bit. And the other bit is you need to know how these anions and cations are distributed. And for that, you need a Boltzmann distribution for the charge, well, the distribution of the charges, which effectively is your elementary charge multiplied by your potential times the valency of your system. So for anions, that would be -1, for example, for chloride, and for cations, it would be +1. So that's why there's a minus sign here and a plus, and not a minus sign there. So those two things need to be combined. So the total density effectively is the total charge distribution of cations minus the anions, so it's your charge density, times the elementary charge times the valency. So let's assume that the valency in this case, you have only like sodium chloride, so +1, -1. So you don't have +2 and then -1 2 times, because it gets a bit more complicated. So if you put that into the equation, you rearrange this and you get the expression on the right, which is a sinus hyperbolicus, which is nothing else than e to the power x minus e to the power minus x divided by 2. So that's why that factor of 2 kicks in there with respect to the thing what we had before. So you basically get your potential in the equation below there was -4 times pi times the charge density divided by the permittivity, and you put, for your charge density, you put the expression in that's given there above. And then you'll end up with that beast on the right. Now, this particular function, if the potential of the applied field is really small, it's effectively linear. So it basically means you can get rid of the sinus hyperbolicus sign. So if you do that, and it's effectively linear, then you get the expression there below. So, which is an assumption for potential, say, smaller than 25 millivolts. Yeah? And this big thing here in front of the electric potential, this is kappa to the power 2. And kappa, or 1 over kappa, is defined as the Debye length. And the Debye length is basically the thickness or the length of the double layer. So what it means, if kappa to the power minus 1 is large, you have a large, well, double layer. So that's basically that charge distribution, the difference in cations and anions, stretches out pretty far. So this would mean that if you would measure your particle size in dynamic light scattering, you get a larger size than you would expect the hard sphere diameter is. Whereas if the double layer is really compressed, you get a smaller extension to that. So the Debye length is an important parameter. So to sum up, you can solve this. So you can basically say, okay, the electric potential then is whatever I have electric potential 0, and the electric potential is the potential at a certain distance. So if I would have two interacting plates here, so I've plotted it here on the picture below. So the charge potential you know, and you move them closer and closer and closer, and what you can calculate is the potential when these two things start to interact with each other. So if you put for two spheres all the equations in there, you get this massive expression that's there given below. So 64 times n times kt divided by the Debye length times this other parameter which is given below here times exponential terms. So for two particular spheres, this exact problem comes down to, in the end, after all this is done, to the expression here below. So to take into account there, so the term here in front is relatively constant, so it scales effectively with exponent minus the thickness of the double layer times d. So it's an exponential drop, effectively. So now you have to combine these two, right? And that's what you end up with the picture in the end. So here you see for two spheres, you have the Coulomb interaction, which is your double layer. So your Coulomb repulsion. And here, this other term, the easiest term here, is on the right-hand side, is the van der Waals attraction. So van der Waals scales with, so if you plot the graph, the interaction energy as function of the distance d, the van der Waals attraction scales with 1 over d, which you can see there, you know, it's the dotted line goes down, and with 1 over d, effectively. And then the other potential here is an exponential drop as function of d, and you can see there the double layer repulsion is an exponential drop that comes there. And then depending on the relative strengths of these two, you basically get a different solution. Yeah? So what you see here is the full potential until you reach this minimum. So the repulsive term, so your Pauli exclusion repulsive term, the r to the power 12 term, is not included in this. That comes before here and shoots back straight up. So for these different scenarios, you can get different solid lines. So the little inset here is given if you would have increasing salt concentration. So at no salt concentration at all, so pure water, your thickness of your double layer is very large, it's relatively large, which means that that term extends pretty far out, which means that that term is relatively important over long distances, which means you get the little inset A. So you have a mountain to climb before you fall into the minimum, which is the reason why you have electrostatic stabilization. Now, if you up the salt dose, you basically start to decrease the size of your mountain. Yeah? And you see here that in case of B and C, you even have like a secondary minimum at longer distances, which could be like reversible flocculation. So they could, from a relatively long distance, assemble a bit and then kick out again, because that minimum is really shallow, so it's relatively reversible. It's only like, you know, KT or maybe, you know, 2-3 KT. So, and then you still jump over this so you still have long-term colloidal stability with some reversible assembly. Now, obviously, if that mountain drops further, at D, at that particular point, at that salt concentration, you hit the critical coagulation concentration. So if you up the dose further, everything just coagulates because there is no repulsive barrier anymore. So the repulsive barrier here is just completely gone. So if you add more salt, you basically compress this term, yeah. So and you get, you basically get completely rid of your electrostatic stabilization. So that is, well, in a long nutshell, how it works. So you have the van der Waals interaction here for two spheres. Depending on the chemistry of the spheres and the medium you produce this in, this could either be attractive or repulsive. So in liquids, for two spheres that are of the same material, it's always attractive. So luckily A is positive. So that's that dotted line. And this big chunk here, which is tough, but it scales with the exponent minus kappa, which is 1 over the thickness of the double layer, times d, which is the distance between the particles. So that's the other dotted line. If you can calculate these two things, you can calculate the interaction potential. So that's what a lot of people, a lot of physicists are doing for a lot of scenarios. Now, this first term here is tough, and people don't know quite often, so they make it easier. So in modeling, people don't use this sometimes because it's too tough. So what they do then is they simplify it, and they use a Yukawa pair potential. So they still have this scaling between the distance of the species, but it's slightly different, and that's the Coulombic repulsion term in that particular case to make life easier for modeling. So a lot of the theoretical chemists that model particle-particle interaction, the end term from the van der Waals interaction is relatively, you can understand with 1 over d, but the electric double layer is really difficult. So quite often they use a different type of potential, which is this potential. So if you read theory papers, you might come across the word Yukawa pair potential, and that's given over there. So, okay.